So let's take a look at section 7.3. First thing we're going to look at is 4 properties with logs. These are kind of special patterns that come up. They're not really anything that you do arithmetic or you try to figure something out. It's like it's a special pattern. And if you see this pattern, you automatically know the answer based on just looking at a pattern. Some of the properties I'll show you why they're true. One of them I'm not going to bother, but I'll show you why most of them work the way they do. So the first one is this expression here. If you've got something that looked like a to the log base a of m, the key is this number and this number have to match. Okay. An example with actual numbers would be like this one. 2 to the log base 2 of pi. That's a very quick problem to simplify because these numbers match. What ends up happening if those numbers match, don't write this part in your notes because you need to be able to read it. But when they match, it's almost like these two things just disappear and they're not there anymore. Okay, they cancel each other out. And the answer is whatever is sitting right there. All right. So as long as these two numbers match, it cancels out, and the answer to the whole problem is what's right there. Right, so it's just a special pattern. We can go through why that one's true if we want, but I'm going to go through why some of the other ones are true, and maybe I'll come back to that one. All right. So that's an expression on the left that's in exponential form. And if you're like, well, wait, isn't there a log? Yeah, there is a log, but it's up in an exponent. So you have a base right here, you have an exponent right there, and you've got something on the other side by itself. So that is exponential form. Versus this one, that's log form. And if you look at it, you're like, well, wait, isn't there an exponent? There is, but it's in an argument. So base, argument, and then that would be what's on the other side. All right. So this special pattern is a log equation, and it's where the base on the log and the base on the argument match. If you want to see like one with actual numbers, it would be something like this. It's a problem where the base on the log and the base on the argument match. And it's kind of the same idea. When those two things match, it's like this all cancels out. And the only thing that's left is what's right there, and that's the answer to the problem. Okay, that one I am going to go through why it's true. All right, so off to the side, I'm just going to write something down, and it's going to show why this one's true. What's my base here? Yeah, A, right here. That's the base. So I'm going to put A. Logarithms always equal what kind of number? Exponent. Logarithms always equal the exponent. So that's my R. So I've used the base. I've used the R. And what always ends up by itself on the other side? The argument. And what's the argument here? A to the R. This box right there. A to the R. Is that what I just wrote by changing that from log form to exponential? Is this true?
That's true.
Why?
Because they're exactly the same.
It's exactly the same. That's just saying something is always equal to itself. That's basically what the second property is. The fancy name for that from geometry is the reflexive property. Reflexive means that something always equals itself. 2 always equals 2. 5 always equals 5. And that's why this one's true. So this is a property you would have learned in geometry, but it's written as a log property rather than like how you would have seen it in geometry. Yep?
Why does that equal R and not A to the R? It says A to the R equals A to the R, but...
Yep, so this is that, right? this is that. So that's my exponent. And then the only thing I have left is the argument. And the argument ends up by itself.
I understand how you get it, but why like you said the answer is always going to be r, but why wouldn't it be a to the r? Like, how does that simplify to r?
So what do you think the answer should be? Let's change it and see what happens. Instead of r, you think it should be
I'm just confused.
A to the r.
a to the r. Okay, let's try it. Don't write that down. Let's pretend that it should be a to the r. Is that what you want me to try? All right. So let's rewrite that in exponential form and see if that's a true statement. What's my base there? A. So that's what's in green. Logarithm always equals what kind of number?
Exponent.
What's my exponent here?
R.
A to the r.
This whole thing would be the exponent. A to the r. Equals. And now what would be by itself on the other side?
A to the r.
The argument, which is right here. A to the r. Now, you can simplify that because when you have a power to a power, you multiply the two together. And that's what that is. That's a power, that's another power. It's kind of like having this. 2 cubed squared, which would mean 2 to the 6th. So this is a to the ar, right? I multiplied those two together, equals a to the r. Are those two things the same? A to the ar equals a to the r? No, they're not the same. So that's why it can't be that. Because if you change it, it just doesn't work. So if you're kind of wondering, well, how would you ever get like the formula on the left from scratch? Like how would you figure that out? Well, you don't really have to worry about it because I already gave it to you, so you'd never have to figure it out. But if you were wondering how, you would start with this. Start with something from geometry you know is true. That's the reflexive property. Something always equals itself. And then convert this backwards to log form. Okay? In fact, that's how I'll do the next one. I usually give the property, but let's start out with something we know is true, and we'll figure out what the property is. I just have to remember what the property is. That one, okay. So I'm going to try to use the same letters. We'll see what happens. If I take and raise something to the 0 power, what's the answer?
1.
1. Anything to the 0 power is always 1. Does everyone agree with that? All right. Let's work backwards from that property, which we know is true, to change it into a property with logarithms. All right. Just put it down here temporarily, but then I'm going to write it out what's under the block. Bless you.
Thank you.
What's my base in that? A. Logarithm always equals what kind of number? Exponent. What's the exponent in that box?
0.
0. And the thing that's by itself here, that's your argument, and that goes right there. That's the third property. So the third property says that if you take the logarithm of 1, doesn't matter what the base is, the answer is always 0. So what's the log of 1 base 0? What about if the base was 0? It doesn't matter. It's always 0. So anytime you take the log of 1, the answer is 0. All right. Any questions on that one? So this is based on a property that you learned way back in like Algebra 1 or pre-algebra. Anything to the 0 power is 1. Okay. Any question on that one? All right, let's do the fourth property the same way. Is everyone okay if I erase that? I need a little more space. All right, what if you take something and raise it to the first power? What do you get?
A.
You get A. Basically, that's just the property saying if you raise something to the first power, it doesn't change it, you just get the same thing back. Well, let's convert that into a log property and see what it says. What's my base here?
A.
Yeah, just to make it clear, we'll do it in a different color. It's the red A. That's my base. So there's my base. What about what goes here? Logarithm always equals what kind of number?
Exponent.
Exponent. So it's 1. So I've used the red A. I've used the 1. And the only thing left is what's by itself on the other side. That's my argument. And that's going to go right here. And that's the fourth log property. It says that if you take the log and the base and the argument are exactly the same, the answer is always 1. So log base 2 of 2, 1. Log base 7 of 7, 1. Log base A of A, 1. So anytime the base and the argument match, the answer always equals 1. All right. So these properties on the left, they might look new, but they're all based on things you already know. The reflexive property, raising something to the first power, equaling it, it doesn't change, and raising something to the 0 power, always giving you 1. So they're just basic properties written a little different. All right, so let's keep those up, and let's see if we can go through some examples. So what I want to do first is just identify which property it looks like. And then once we know that, we'll use the property to simplify it. How about 1A?
First.
Yeah, that's the first property. So if you were to simplify it, what would that whole thing simplify to based on property 1? Pi. Yeah, the answer is just pi. Now, we didn't go through the proof of that property. I could have, just like the other ones. It's not that hard, but it's not really critical. Okay. Any questions on that one? All right, let's look at B. What property does that one look like?
2.
Yeah, that's property 2. It's a log where the base on the argument, the base on the argument and the base on the log are exactly the same number. So when that happens, we went through the proof. It's like the reflexive property. What would B simplify to? Yeah, -4. All right. How about C? A little tricky, but it is one of the properties. Anyone think they see what property it is? Yeah?
Is it the second property?
Yeah, second property. How come? It doesn't look exactly like the second property to me. Yeah?
Because it's log base 10 of KT.
Can you say that part again? What's just that part?
Log base 10.
You're on the right track, but not quite. If it was, well, I won't say anything else, but not quite. What's the ln again?
Log E.
Now you got to take the two things you said and put them together. She said log base 10, you said log of E.
Log base 10 of E.
Log E.
Not quite. Close.
Log base E.
Log base E. ln is log base E. So if you take this and just rewrite it as log base E, that's just the circle part. This is kind of like the one in the homework. And now the argument is e to the kt. Now I can tell that that's definitely property 2. The base on the argument and the base on the log match. So what, the way I'm using property 2, what would the answer be? Kt, whatever k times t is, we don't know. But if k and t were numbers, we could figure it out. It's k times t. All right, let's do one of the other ones I didn't do. Let's do log base 6 of 1. What would the answer to that be? Log. Yep. Anytime the the argument is 1, doesn't matter what the base is. The answer is always 0, and we went through the proof why. And let's just do log base 12 of 12.
1.
Yeah, the answer there would be 1. And that goes back to the idea of raising something to the first power as itself. That was the proof. So property 4 says the answer is 1. Okay. So once you go through the reason why, there's not really any arithmetic with any of these properties. It's just a special pattern. When you see it, you automatically know the answer. So these 4 properties, probably good to put on a reference sheet. Questions on those? Okay, so that's the first part, looking at those special properties. Okay, second thing we're going to look at is how we can take logarithms and either combine them together or take something that's already combined and split them. So I'm going to go back in a second, but this is an example of a problem where you want to take what they're giving you, and we're going to split it into 2. This is an example where they're giving you a problem where you have 2 separate logs, and they're going to want you to combine it together into 1. So we're going to go through the properties for how you can do that. Does anybody already know the properties? There's really 3 basic ones. All right, so let's look at the first one. The first one has to do when you have the log of a product, like m times n, or 3 times x, could be anything. When you have the logarithm of a product, it can split apart into 2 logs. Notice the base on when you split it is exactly the same as the base that it started out with. The base never changes all the way through the problem. But a product splits as a sum. So product turns into a sum. I have 2 logs. The first argument is my first factor. The second argument is the second factor. And if you had a third one, you could do something like m times n times x, and then do plus log base a of x. You can do as many as you have. I'm just doing it for 2. So there's an example with numbers. Okay. Log base a of 4 times 5 equals log base a of 4 plus log base a of 5. Okay, and I'll show you that one on the calculator. Now, for me to type it in on the calculator, I have to pick a number for the base. The base doesn't matter. That's what I'm trying to show you. The base can be anything. It doesn't change the property. But if I want to do it on the calculator, what's one base that the calculator can do? It can do e, so I could type in ln. Or what's the other base it can do? 10. So I could just press the log button. So I could do it either way. For this one, I'll do base 10. So let's pretend a equals 10. So if I do the log of 4 times 5, which is just 20. So that gives me that number. Now if I do log 4 plus log 5, I get exactly the same thing. What are 2 other numbers that multiply to give you 20, besides 4 and 5?
2 and 10.
2 and 10. So log 2 plus log 10. Any 2 numbers that multiply to give you 20, if you use this property, you'll always get the same answer. You could do 40 and a half. You could do that, that would work. Anything. Okay, but the point is a product changes into a sum. So the next one has to do with a quotient. Any guess on what a fraction would change into?
Subtraction.
Yep, it's going to be subtraction. Very good. Now this time the order is important. So when you have a quotient, it's the log of the numerator minus the log of the denominator. With addition, the order isn't as important because when you add 2 numbers, you can add them in any order. When you subtract them, you got to do it that way. Okay. And here's another example with numbers. I'm not going to type that one in, but if you wanted to check it, you could. And then the third property It's kind of like the first property, except, well, I'll show you. We're going to see if we can figure out the rule for the third property using the first one. Okay. Everyone have those two? All right. So let's say I have the log of y times y. Actually, let's do it this way. Start out with this. The log of y cubed. Okay. I want to see if I can come up with some way to simplify that. Let's just start by writing it out. For somebody that didn't know what cubed meant, how would you explain what it means to take a y and raise it to the third power? What does that mean? Yeah.
Y times y.
Right, it means y times y times y. Now, what I really have here is rule 1. I have a product, and a product changes to a sum. Multiply two things, sum of two things. Multiply three things, we're going to have a sum of three things. Right? So let's write that down. When I do this, put your plus signs. Does the base change when I split it from what it was originally? No, the base stays exactly the same. What base am I using here, by the way?
1, 10.
I'm using base 10. I'm not writing the 10. I could use any base I wanted. The base is irrelevant. So log, log, log. What's my first argument going to be?
Y.
Y. It's my first factor. What about my second argument?
Y.
My second factor.
Y.
I'll just put these in parentheses so they look clearer. And then what about my third argument?
Y.
Y, which is my third factor. Now I've got log y plus another log y plus another log y. What would that equal if you added them all up?
3. 3 log y.
Yeah, you have 3. It's like if you did x plus x plus x, you have 3 x's. Well, this is log y. So you have 3 of the log y's. Now, look at what we started with. Look at what we ended up with. And we should be able to jump right from that top box to the bottom one. What happened if you just look at the top box and the bottom box?
Just
You just moved the 3 where?
behind the log. In front of the log.
In front of the log, yes. All you have to do is take that 3 and move it in front. So anytime that you have an exponent on an argument, you are allowed to a log function. You're allowed to put the exponent in front. And that's the third property. So now we won't have to go through writing out something like y cubed is y times y times y. We can just use this shortcut. Take the exponent, put it in front. Okay, here's another example. If you had the log of 3 to the 5th, that's the same as 5 log 3. Or base 10 if you want to pronounce that. But you don't have to, because if you don't pronounce it, everyone's going to assume it's base 10. Now, there's one little trick with rule 3 that you have to be careful of. And that's if you had something like this. The log of the square root of x. And if I said to you, I want you to rewrite that without any exponents. And if you look at that and say there is no exponent, well, there's no exponent written, but square root does mean that it's an exponent. It's like it's hidden. Does anybody remember what power represents a square root? It's not 2, because 2 is squaring. That's the opposite of a square root. What is it?
1 over 2.
Yes, it's 1 over 2. So anytime you have a square root, I think I write that down here. A square root is really hiding a 1/2 power. Just like a cube root hides a 1/3 power. A 5th root, 1/5. 12th root, 1/12. we're not really going to have to deal with those other ones. You're just going to have to worry about square root. So if you have a square root, it means this. And then you can take this and put it in front. So the log of the square root of x, if I said to simplify that without exponents, I'd be looking for this. You got to know that the square root means 1/2, and then you can put the 1/2 in front. Any questions on that one? Always one that trips people up on the test. Right. So now we'll just use these three properties, the one for the product, the quotient, and the exponent, and see if we can either combine logs together or take and split them apart. All right, so read the directions carefully. It says write as a sum or difference. So that means take what you have here and split it up into multiple things, either sum or difference. But it's that last sentence, express all powers as factors. What that means is don't leave powers in the problem. Don't leave powers in the final answer. Move them in front. Because when you move it to the front, it changes to multiplication, and that means it's a factor. So don't leave exponents in the final answer. If the problem even has exponents, this one doesn't. The next one will. Okay, so let's look at that. Log base 4 of 3x. How is that logarithm going to split? As a sum or a difference? Yep. It's going to be a sum because it's 3 times x. So we're going to have a sum of 2 logs. What's going to be the base on each log? Oh, Oscar?
4.
Yeah, the base never changes. So whatever it was to start with, that's what you keep it all the way through. And now what about my first argument? Mike?
3.
Yeah, first argument is 3. It's my first factor. And what about my second argument? Yep, x. And that's it. Now, by the end of the lesson today, you're going to know how to type that in on a calculator. Log base 4 of 3. Okay. We don't know how to type that in yet, but you could type that in and get an answer. Okay. But not yet. Questions on that one? All right, let's try this one. Log base 2 of 5r cubed. Joe, does that one split as a sum or a difference?
Difference?
How come?
Yes.
Yeah, sure. Anyone agree that it splits as a difference, or and then tell me why, or if you don't agree, tell me why. Because I forgot how to do it, so I need help. My mind just went totally blank. Yeah.
Wouldn't that be like the third one? Because it has the exponent.
All right, I think the third one is going to come in there somewhere. If there's something you have to do before the third one, in terms of the order of operations kind of thing, you always do rule 1 or 2 first, and then rule 3 would be last. But yes, rule 3 is going to come up.
Wouldn't it just be a sum?
How come?
But it's multiplication.
Right. It's still multiplication. Bottom line is it's something times something. You're multiplying 2 things together, so it is a sum. So log plus log. Christian, what's my base on each log?
2.
2 and 2. And my first argument, Eric, what's my first argument?
The 5 times r, or just the 5?
Just the 5, yeah. So 5 is the first argument. And what's the second argument? There's a couple things you can do, but you don't have to do both yet. What would it start out as? Yeah?
Wouldn't it be 3 log 2r?
Yeah, it would start out as r cubed. But then the directions say not to leave powers, so the r cubed, the cube would go where the 3 would go in front. And that's how you do that one. Any questions on that one? All right, let's look at the next one. Log base 9 of x over 2. How is this one going to split?
Subtraction.
Yeah, why is this one a difference?
Because it's dividing.
Because it's dividing. Okay, because it's dividing, it's a difference. So it's a difference of 2 logs. What's the base on each log? 9. So base 9, base 9. My first argument,
X.
and my second argument,
2.
2. And that's the final answer. Now this first part, there's nothing you could ever do with that unless you knew x. But the second part, once we know how to type in other bases, you could get a decimal for that. They wouldn't ask you to in a problem like this, but you could. Okay, let's try this one. The ln of y cubed over 8. Remember, the properties I showed you, doesn't matter what the base is. 2, 10, 3, 9, or even e. Right? We're not going to write it as log base e, we're just going to stick with this abbreviation. So the final answer is just going to be all ln's. Just use whatever they gave you to start with. So if they used log base 9, that's what you use. If they used ln's, that's what you use. Okay. Anyone think they could tell me the whole thing? Yeah?
3 ln y minus ln 8.
Yeah. That's it. So it's a difference because the original problem had division. It's going to be the top minus the bottom. The bottom is nothing you can do, but the top is y cubed, and the direction said to put that 3 in front. Okay. Questions on that one? All right. Let's just jump right to this one. So this has got everything in it. It's got all kinds of stuff. The easiest way is just to do it one step at a time. Okay. When I look at that problem, this is basically what I see in the argument. I see one thing in the top divided by, and I see 2 things multiplied together in the bottom. That's how I look at it, like big picture. Okay? So anytime that you have a problem that has both division, which you've got right there, and multiplication, which you've got right there, always handle the division first. And how does division split? Sum or difference? Difference. So that's the very first thing I'm going to do. I'm going to split it as a difference of 2 logs. Base stays exactly the same. Probably gonna need a little more space. And it's going to be a difference of what's in the top minus what's in the bottom. So that's what's in the top. Square root of x squared plus 1. What's in the bottom? X cubed times x plus 1 to the 4th. That's the first step. Any question on that step? Now I've got 2 smaller problems. I've got the first one, and then I've got the second one. Let's start with this first one. What can I change there that we mentioned earlier? There's something in there that's hidden.
1 over 2.
What do you mean 1 over 2?
How would 1 over 2?
Yeah, there's a power of 1 over 2. Where is that coming from? I don't see a 1 over 2 in there. The root, right? So this is really x squared plus 1 to the 1/2. Now at this point, there's only one more thing you have to do, and then the first part is done. So we'll handle that in another step. Now, look at what we have here. When I look at this second part, this is what I see. Log something times something. When I have a sum of two things multiplied together, how do I split them?
Did you forget the base right there?
The base, oh, yes, thank you. Not a huge deal, but yeah, we should put it. It should be there. How do we split a product of two things? Yeah. You add them. So we're going to have
Wait, so where did the 1/2 come from?
from the square root.
Oh, yeah.
Yep, it's hidden in the square root. Think of it that way.
Yeah.
All right, so now when you take all this stuff and split it apart, you have to remember that however you split it, you're subtracting all of the stuff that you split it, because that's what it looks like right now. You're subtracting all of that stuff in green. So that's why I'm putting a bracket there. So when I split it, I'm going to have two logs, and Skylar just said it's a sum, and I'm subtracting both of them. Okay, I'm subtracting all the stuff that was in green, even if I write it a different way. So that's x cubed, base of a, and the second one is x plus 1 to the 4th. All right, so now we're at the last step, which is basically to do the same thing 3 times. What's the last thing I have to do there? Put all the exponents in front, which if I was doing it, I probably would have just done that in the last step. It's 1/2 log base a, x squared plus 1. And now if you look at that, you're like, well, can I do something with that? No. We don't have a rule when it's a sum. We have a rule when you multiply two things together. We have a rule when you're dividing two things. Not when you're adding. Okay, there's no rule for that. So that just stays the same. And then the 3 goes in front. Plus, and then the 4 goes in front. Fix that. 4 log x plus 1. Why did I leave parentheses around the x plus 1? Why not just do it like this? Parentheses are kind of important there. Yeah?
So that's log of x plus 1. Like log of x plus 1 after it.
Yeah, so
Log of
the
x plus 1.
difference is basically, are you doing this, log of something plus 1, or are you doing this, log of something plus 1? That's kind of the difference, okay? This x plus 1 was all part of the argument. So if you put parentheses there, then somebody looking at it knows that, okay? Because there was parentheses with it when you started. So just leave the parentheses. And that's it. That's the final answer.
Doesn't there have to be a after?
Yeah, I keep forgetting that base, sorry. Yeah, you should keep the base the same all the way through the problem. Yeah, if it was a multiple choice question and you forgot the base, you'd probably catch your error because all my multiple choice answers are going to have the base on them. So, all right. So now let's look at the same thing, except in reverse. So now you're taking like what your final answer was in the last problem, and you're reversing everything to put it all back together. Okay. What would be, you think, the first thing you would have to do here to start putting everything back together?
Whatever's in front of the log, make the exponent.
Yep. So you're going to put numbers in front, back as the exponent. So it's log base a 7 plus log base a of 3 to the 4th. Now we should do that out, because if you've got 3 to the 4th power, you can simplify that. So we'll do that. What's 3 to the 4th power? Yep, 81. If you're kind of stuck, just think of it as, well, it's 3 times 3, which is 9, and then another 3 times 3, which is 9. So 9 times 9 is 81. All right, So now my two arguments are 7 and 81. I'm going to put them back together as a single log. How would they be recombined? We have addition. So what does addition turn into? Multiplication. 7 times 81, which is 567. And that's the final answer. Log base A of 567. Any questions on that? All right. Let's try this one. Let's move it down. Let's see if we can do it all in one step instead of writing out like 3 steps all separate. So we're going to have one log. What's going to be the base?
3.
3. That doesn't change. Anyone think they can tell me what the argument would be?
U squared. U over V.
Close. I like the fraction part. That's good. But it's going to be u squared over v. Any question on that? Now, sometimes in the homework, you might see something like this. You might say u is greater than 0 and v is greater than 0. That's because, remember, whenever we're taking logs, we can't use negative numbers. Right? We mentioned that yesterday. So if you see this in the homework anywhere, don't get confused by it. They're just saying that we're not using imaginary numbers. Right? It doesn't really mean anything significant. All right, let's try this one. I need to change this a little bit though. Let's see. Actually, you know what? I think that's fine. Let's just leave that. All right, so first thing you do here is put the 2/3 back as an exponent. Now, 8 to the 2/3, we can actually do that in our head. Notice how I wrote it as a fraction, but I wrote it kind of horizontal? That was on purpose, because if I think of it like that, it's 8 squared, which is how much?
64.
It's 64. And then the number you divide by, that tells you the root you're taking. If it was a 2 in the bottom, that's a square root. We did that earlier. That's a 3 in the bottom, so that's a cube root. So you've got 64, and now they want the cube root of 64, which would be how much? Yep. 4. Yep. I mean, you can always type it in on a calculator, but the numbers, they came out nice this time. So 8 to the 2nd power is 64, and you take the cube root. Okay, so that's the first part. Minus 3 to the 4th. We just did that in the last problem. What was 3 to the 4th power? 81, and then minus 8. Well, see it?
73.
Yeah, 73. So now we're one step away from having that all together as one. What would be my final answer? Corey?
ln 4 over 73.
Yep. ln of 4 over 73. Question on that? All right, so let's look at the last one. So when you look at it at first, it kind of seems like it could be really awful, but it's you're going to be able to do this all in one step. When I combine that all into one log, what's my base going to be? A. Now I have plus and a plus. When you have pluses, what do you do with the arguments to combine them together? Well, that's what they are now, but when you combine them, it's not addition. Yeah. You're going to multiply them. X times 9 times x squared plus 1. How come I'm not saying times 5? Because that's a minus. That's different. So x times 9, well, we normally write that as 9x times x squared plus 1. So it's 9x times x squared plus 1. What does the subtraction mean? Divide. And what are we dividing by? Yep, I made that a little too big. Divided by 5. And that's it. The only thing they could do in the numerator, they might or might not do it, is you could distribute the 9x. What would you get if you did that? What's 9x times x squared? 9x cubed. And then 9x times 1 is just 9x over 5. So they could do it that way too. The same thing. Okay, and that's pretty much as bad as it can get for recombining logs. Any questions on that one? All right. So, last thing we're going to look at is how can you type in a base that's not 10 or e. That's the only ones the calculator can do by pressing a single button. But there is a way to type it in on any calculator. Some calculators have different features built in, like if you have a graphing one. I can go to this feature, 5, and I can actually type in logs that have a different base. Log base 8 of 42. That's how I can type it in. Not every calculator has that feature. So I'm going to show you how to type it in on any calculator, especially mine. Mine don't have that feature. Okay. All right, so let's start with that equation. I want to figure out what y is. That's the goal. How do we figure out y? Well, the problem is going to be if a is not equal to 10 and it's not equal to e, you don't have a button for it. So what I need is I need a different formula. I need another way to figure out y using the buttons I already have on the calculator. Right. So the first thing I'm going to do is I'm going to change this to exponential form. What would that look like if I rewrite it in exponential form? Yep.
It would be a to the y power equals x.
Yep, perfect. A to the y equals x. Now my goal when I'm done is to get y by itself again, but not like this, because what's in the box, that doesn't help. I don't know how to type that in. I got to get something different, something that the calculator can understand. All right. Now the next step is a little tricky to figure out. But a hint would be, I would like to get rid of this y as an exponent. We can't get rid of exponents, but what can you do with them? This was one of the properties we learned today. You can move them in front, but you can't just, like if you had this, you can't just say, oh, that's the same as just doing 2 times 3. You can't just take exponents and put them in front, unless you have what kind of equation? A log. Okay, the only time you're allowed to put exponents in front is if you have a log equation. So let's just take the log of each side. Take the log of what's on the left. Take the log of what's on the right. Now you just created a log equation. And if you're like, well, how can you just do that? Well, it's kind of like if you had this. And you said, I'm going to take the square root of both sides. Sure, as long as you do it on both sides. If you want to take the log of both sides, it's fine. Just do it on both sides. Now, what can you do with the y? Now you can put it in front. So I have y times the log of a equals the log of x. So what I've got now is something like this. Y times something equals something else. How would I get y by itself? Divide by what? Divide by log a. Divide by log a. And divide by log a. That's gone. So now you have a new formula. We've just got y by itself again. The new formula says y equals log of x over log of a. Now, there's no base on the log. So what base am I assuming if it's not written? 10. I've got a formula for y that uses base 10. Is base 10 something I have a button for? Yes. So now I've got a new formula for y using logarithms, but the base is now something I have a button for. That's how you do it. Now, look at what's in box 1, and then look at box 2. How could you, without going through the work in between anymore, how could you just change what's in box 1 to box 2? What's the shortcut? Yep. And what's x? It's the argument. So it's the log of the argument divided by the log of the base. That's how you change it. And it doesn't matter what log you use. I used base 10 log. You could also do this. You could also do this with base e. She said log of argument over log of base. You could do the natural log of the argument over the natural log of the base. It comes out exactly the same. I'll show you it comes out the same on one of them, but I would just pick one of those two and go with that. So this is called the change of base formula. Either way. Log of the argument divided by log of the base. Let's try it. So I want to know what the decimal is. We'll round to 2 places. Okay, so first thing I need to do is I need to rewrite that. I don't have a button on the calculator for base 5. So I can rewrite it as a fraction. And what would go in the top? What would? Log of 12, yep. And what would go in the bottom? Log of 5. And that's, once we type it in, that's the answer. So log of 12 divided by log of 5. So it's about 1.54. Now, what if you used ln? ln of 12 divided by ln of 5. It doesn't matter. Use whatever log you want to use. Just make sure you're consistent. If you use log in the top, use log in the bottom. Don't mix log in the top and then put ln in the bottom. That won't work. Use the same ones. So 1.54. All right, and let's try this one. Dylan, can you tell me how I would rewrite that one?
Log 16 over log 3.
Log 16 over log 3. Now he just said log, so what base is he using?
10.
He's using 10. If he had said ln, he'd be using e. Doesn't matter which one you use. Log 16 divided by log 3, and that's the correct answer, 2.52. What's happening when I do this? Log 16 divided by log 3. I get a different answer. How come?
You're doing 16 divided by log 3 and taking a log of that.
Yeah, this is correct. That's wrong. That bottom one is doing this. The log of 16 divided by the log of 3. It's like you've got a log inside a log. No. You want to do it the top way. Okay, so we started out, we took a look at those 4 special properties, just patterns. Then we looked at the combining and splitting of logs. I like combining it better because then it gets simpler at each step. When you're splitting it, it gets worse at each step. It gets like bigger and bigger. So I think combining is easier. And then the last thing we looked at is the change of base formula. So now you know how to type in a log with any base. Okay? And just like the argument, the base cannot be negative. Okay? Bases and arguments always have to be positive numbers, unless you're dealing with imaginaries, which we're not. Okay. Any questions on that? All right. So homework tonight, it's on the same page as last night. Just no, I'm sorry, it's a different page than last night. It's page 485. It's 7 to 15 odd, 31 to 33 all, so 31, 32, 33. And then 39, 40, 51, 52, and 65 to 69 odd. So we'll take a look at that tomorrow. We'll finish up everything with logs, and then we'll have our test. Bless you. Test on Thursday. Bless you.
Thank you.